Hello, this is part two of our tangents and secants videos. Just a quick reminder on what a tangent and a secant is. A tangent is a line that touches a circle exactly once at that point of tangency there. And a secant is a line that touches a circle twice. So it can go in and come back out. It has 2 points on the circle. All right, we're going to focus on part two. We're going to focus on the segment lengths that happen with tangents and secants. So the previous video, if you haven't watched that one yet, I would definitely watch that one first. It focuses on angle relationships. We're going to focus on segment relationships with tangents and secants and intersections and chords. And that's where we're headed today. All right, so here we go. Heading down. And now you may have this chart in your notes if your teacher provided you with it. If not, feel free to pause the screen and make this chart so you can have some notes that go along with the examples that I'm going to talk about today. Okay, so I'm going to use this chart as a way to introduce some theorems that go along with behaviors here. I'm going to use a lot of vocabulary like secant, tangent, chord, intersection, and hopefully that'll help you understand what's that exactly going on here. Okay, so our first scenario is if two chords intersect in a circle. Now remember, those chords would be parts of secants. So if I drew secants, that would create this same scenario. But two chords intersecting inside of a circle, not necessarily going through the center, not necessarily working with diameters here, just what does happen when you have two chords intersect inside of a circle. And unfortunately, it's not as good a relationship or as simple a relationship as they just bisect each other. But an interesting thing does occur. The product of their parts is the same, which is very interesting. So that means you multiply the length of each portion of the chord, and that is going to be equal to the product of the portions of the other chord. So what we mean in this case, we mean that 6 times 4 is equal to x times 2. 6 went with 4 because they're on the same chord. They're the two parts. And then x and 2 went together because they're on the same chord and they're the two parts. So you multiply those together and solve for x. 24 is 2x. Divide both sides by 2. And x must be equal to 12. All right. That's our first scenario. Second scenario. If two secants from an exterior point. So that means you've got secants intersecting outside of the circle. So hopefully you can see that real quick. Two secants intersect outside of a circle. It's not going to be the same relationship where part times the part equals the part times the part of the segments, but you do get something interesting. So what you end up with is this idea of outside times whole equals outside times whole. And that's going to be a common theme with the next scenario as well. Outside times whole, outside times whole. So back up. The first example, the two segments intersected inside the circle. Now we're talking about intersecting outside the circle. Outside the circle. All right, so if they intersect outside the circle, then you get this outside times whole equals outside times whole relationship. All right, what are you talking about? Outside of, and I'm going to focus on this LO first. All right, so we're talking about this guy right here, focusing on him. All right, what I mean by outside times total is the outside portion is LG, and that is 2 units long. And the total is going to be 10 plus 2. So outside part 2, and then the total is the two things added together, 10 plus 2. And that's supposed to be equal to, for the other scenario, and I'm talking about this segment here, all right, that's supposed to be the outside part, which is x, and then the inside plus the outside, which is the total, 5 plus x. Okay, so that's the relationship. That's how we'll solve that. And what you want to do there is you're going to try to distribute and you realize that it's going to be a quadratic equation, so you're going to have to solve that. I'm going to set up the next example first, and then I'll backtrack and solve just to make sure we do that review of quadratics real quick. So the next scenario is a tangent intersecting a secant outside, but again, that focus on it intersects outside is the big thing. So outside times total equals outside times total. That's what you're thinking. Well, interesting enough, in this first segment down here, and again, I'm on this example here, the entire segment is outside. So when I say outside times total, I end up doing the outside 7 times the total 7, because the entire segment is a tangent, and that tangent only is outside the circle. It doesn't go in because it only touches once. So outside times total equals outside. So I'm looking at this next segment here. The outside portion is 5. And then if you notice here, they tried something a little bit different on us. They told us that the entire segment of MC was X. So I don't have to do any adding. They just went ahead and found that total thing for me. So it's just going to be X because they gave me the total. If they didn't do that, if they gave me a number for BC, then I would just add them together like I did on the previous example. So then if you multiply that, 7 times 7 is 49. Equals 5 times X, divide both sides by 5, and it's okay to get a decimal here. Some of you guys might freak out a little bit. It's not a problem. It's okay to get a decimal here. So then you end up with 9.8 if you prefer decimals, or you could just keep your 49 over 5 for an improper fraction. So that's how we would solve for that. Okay, again, both of these examples that I did together are intersections outside. So that means you do an outside times total equals outside times total. That's different from our first example where they're intersected inside the circle. And inside the circle, different ball game, part times the part equals part times the part. All right, a real quick refresher on quadratic solving. I'm just going to do that with you just so you have that exposure. All right. So work my way from the inside out on these things for my numbers on the left side anyway. That's going to end up giving me 2 times 12, because 10 plus 2 is 12, and that's going to give me 24. All right, I'm going to have to distribute that x, so that's going to be 5x plus x squared. Now, as soon as you see that x squared, you're thinking quadratic, you're thinking set it equal to 0 and try to factor, or you're going to have to use the quadratic formula. All right, so subtract 24 to get everybody on the same side there, and I've got 0 is equal to x squared plus 5x plus 20, or sorry, minus 24. Almost made a mistake on that one. And now I'm going to try to factor it. So I'm going to notice that that lead coefficient, that a value is a 1. So that's good news. So I'm going to try to find the factors of negative 24 that add up to positive 5. So which numbers multiply to give me negative 24 but add up to positive 5? So real quick, I'm going through that in my head. And I'm thinking, okay, negative 24 and 1 or 24 and negative 1. That's not going to do it. They don't add up to 5. Then I've got negative 12 and 2 or 12 and negative 2. That's not going to do it. They don't add up to 5. Then I'm starting to try maybe negative 8 and 3 or 8 and negative 3. Well, negative 8 and 3 add up to negative 5, but look at this. 8 and negative 3 do indeed add up to that positive 5. So those will be my factors. So over here, I can rewrite this as a product of x plus 8 and x minus 3. Then I'm going to set each factor equal to 0 so I could solve for my two x values. So x plus 8 is equal to 0. So x must be negative 8 when I solve. And x minus 3 is equal to 0. So x must be positive 3 when I solve. And that's how I would solve for those two scenarios. Now, a real quick check to make sure this is reasonable. You take a look and you see, geometry, actual lengths. Can x actually be negative 8 units long? And you're like, no, probably can't. So I'll take that out. Can't have negative distance. And then I do end up with one answer. But you only know which one is the correct one once you get the two answers and then check and see which is your reasonable answer. All right, to close out our video, I've got two more little baby theorems to share with you, a couple of behaviors with these segments that I do want to share. The first one is here in blue. This is two tangents drawn to the same circle are congruent. So the length of this tangent is congruent to the length of that tangent because they're drawn from the same exterior point to the same circle. From the same exterior point to the same circle. Two tangents, they have to be tangent, same exterior point to the same circle are going to be congruent. So x had to be equal to 9 in that scenario. The next scenario is two tangents, a tangent intersecting a radius or some part of a radius. And remember that a diameter contains a radius. So if a tangent intersects a diameter or a radius or a part of a diameter, then it's going to create this relationship here. If a tangent intersects a radius, they are perpendicular, which means they form a right angle. So you can see this relationship here with this line AB, and it intersects segment AC at the point of A. That's your point of tangency. If a radius and a tangent intersect, they form a right angle. So the measure of that angle CAB had to be 90 because line AB is a tangent and segment AC is a radius. A radius and a tangent intersect at a right angle. So there you go. Those are your relationships there. Making sure if you need to go back and pause your screen and write anything down, go right ahead, rewind. Good luck. Thank you for listening.